Okay, so we're going to pick it up where we left off, which is actually, we didn't quite finish talking about the formation of the solar system. So I'm going to do that, and then we'll move on to talking about the sun. All right, so I'm actually going to just briefly review the condensation theory. Now, there is a step before this called the nebular model, which is basically just a big cloud of gas that collapses down under its own gravity, if you recall. The problem with the nebular model was that there wasn't enough cooling in the gas, so that when the gas collapsed, it couldn't actually form planets, because as the gas collapsed, it heated up, and that created extra pressure. Very much like trying to compress a spring, really. If you compress a spring, you can compress it, but it's going to expand again. Well, the gas acts like that in the nebular model because it doesn't cool off, so it keeps its pressure, so it's like squeezing a balloon, it's going to bounce back. What you want to do here is squeeze the balloon gravitationally and have it not bounce back, but just continue to collapse. So the condensation theory achieves that by adding dust to the nebular model, which is, again, just sort of an odd thing if you just think about it from an everyday point of view. But if we do that, as I mentioned last time, there's two benefits that come into play. One is we actually are able to achieve this cooling I'm talking about, because remember that the picture in your mind, a disk of gas around the early sun. So that disk of gas is being illuminated by sunlight. But the sunlight's not able to escape through the gas because the gas is basically a thick-looking cloud. So the difference that the dust makes is it takes the energy that's received from the sun and re-radiates it as infrared. And infrared is able to escape from the cloud now. Okay, so that actually becomes a way that the cloud can cool, and thereby, if you think about squeezing the balloon again, the balloon would be like a blob of gas in this cloud. Well, now when you squeeze it, there's dust in that balloon too. And that's actually achieving cooling by emitting infrared. So now the balloon doesn't bounce back, it collapses. And also, the dust particles act as condensation nuclei, which help the whole formation of primordial small objects take place, which then are agglomerated into larger objects. Now, one thing I didn't mention last time, which would be a good question, is, well, where is this dust coming from? I mean, you can't necessarily snap your fingers and say, let there be dust, and that'll solve our problem. You know, there has to be a physical reason for it to be there, hanging around in the neighborhood of this cloud. And actually, it turns out that in the hundreds of years since the nebular model was developed, we now understand stellar structure and evolution a lot better. And in fact, stars do generate dust. And so the interstellar medium has dust in it. So that's where the dust comes from. It comes from other stars that have gone through active periods when dust was formed in their outer atmospheres. Okay, so the basic steps in the condensation theory, you start with that big, well, you really start with a ball of gas about a light year across, a trillion miles across. When we get to that top panel up there, that's already shrunk down to maybe 100 astronomical units or so. Much smaller than the original cloud already when we get to that top pancake. And that's why it looks flat, because again, this rotational centripetal force keeps it from collapsing in that direction that's perpendicular to the spin axis. But vertically, along the vertical spin axis, there's no such centripetal force, so it's just flat like a pancake. So we also have a speed up. Remember, we have a speed up of the spin that takes place, and that increases the centripetal force. Eventually, we form into these protoplanetary blobs, those little white things, which are basically snowball-sized objects, which can stick together and form larger objects. And then this is, again, this process we call accretion. Things bump together, and they stick together, and we get larger objects that we now call planetesimals, which are objects that are probably a little larger than Pluto, something like that. So these are large enough to start to attract each other gravitationally. And in the outer solar system, we expect something a little different takes place, because we have to have a massive kind of an iceberg to attract the hydrogen gas. Oh yeah, one other thing to mention is that this isn't necessarily a one-way process going from left to right, because it also has all kinds of violent collisions taking place. So you can have accretion that leads to the accumulation of these masses that we call protoplanetary masses or planetesimals, but then they can get smashed apart again. So it's a kind of one, two steps forward, one step back kind of process. And in order to achieve the regular planetary orbits that we see now, which have small eccentricity, what we need to do is combine together thousands and thousands of planetesimals that individually have very erratic orbits. But when they combine together, the erratic qualities of the orbits tend to cancel each other out, and we get low eccentricity orbits for the planets that we see today. And again, the leftover material was formed in place in the Kuiper belt, and also was flung out into the outer solar system, into the Oort cloud, and into the inner solar system. Okay, again, just wanted to reemphasize, in the outer solar system, we have to recognize that there's this kind of chicken and egg problem, because you want to have enough of a mass there to attract hydrogen, but you don't start with that big a mass. So how do you bootstrap your way up? Well, we think that actually occurred by way of eddies that were swirling around the outer solar system, which allowed more massive amounts of ice to accumulate, leading to really large planetesimals out there, a few really large ones, which now are able to hold on to hydrogen gas for two reasons. Remember, there's always at least a couple of reasons why we keep an atmosphere. In this case, it's because if you're talking outer solar system, the temperature is low, the gas velocity is low, and these iceberg type things I'm talking about are massive enough that their escape velocity is actually higher than this hydrogen gas velocity. So that's the key to actually being able to get something like a proto-Jupiter to start sweeping up hydrogen. If you don't get to a mass that's high enough that you have a high escape velocity, then you're not going to be able to carry out this scenario I'm talking about. All right, so this is kind of a lot of words here, but we've already talked about a lot of this stuff. There's accumulation or accretion, as we call it, and there's also fragmentation because of these millions of very high-speed collisions taking place. Smaller objects can accumulate or break up into meteors, it says. And it was a rather efficient process. Over 99.99% of the matter that was available was actually used to make planets and moons. But a little bit remained, and that actually formed asteroids and comets, as we see. Very tiny fraction. Again, if we add up all that leftover material, it's less than the mass of our moon. So that's how incredibly efficient this process of planetary moon formation actually was. Okay, so the regular spacing that we see when we look at our planets and even some other solar systems is recovered in computer simulations, but not the precise spacing that we see in our solar system, but something that looks sort of similar. And again, we see a period of pretty rapid formation of planets, followed by about 1 billion years to clear out the debris that's left over. We've talked about differentiation of the solar system again. This is a plot where, again, we're looking at the temperature in the early solar system. This is not the current temperature, it's the temperature around 4.5 billion years ago. And the reason, again, that this is very important is because what we're seeing here is that at Earth's distance from the sun, at that time, it was much too warm for water ice to form. So obviously Earth today can have ice on it, but at that time, no, it could not have ice on it. So the ices tended to form in the outer solar system, and that's why we see very icy objects in the Kuiper belt, because it was cool enough out there to form icy materials. Near the Earth, we have the rocky silicate materials, some iron. All right, so that's the way it was then. I decided to actually add to this a curve which I calculated based on the current brightness of the sun. You can actually calculate what the temperature is of any object that you put out in the sun in space. It's actually very similar to the things we've already done this semester. If you take an object like this, oh no, this pack of Keebler cheese and peanut butter crackers I happen to have lying here. Okay. I don't think these had ever gone into orbit. I mean, not this specific pack, but anyway. You put this out in the sun, put the vectors of the sun. Okay, so it's sitting here, it's getting illuminated by the sunlight. It's going to heat up to some temperature, right? And the reason it heats up to a certain temperature, it doesn't just keep heating until it explodes. These are actually not toasted cheese peanut butter crackers, so they could theoretically toast. But remember that what actually happens is it's going to heat up until it emits its own black body spectrum, this Planck radiation we talked about, so that the energy it's emitting is exactly equal to the energy it's receiving from the sun, right? But it doesn't emit the same kind of waves that it receives. Like right now it's receiving sunlight, right? So we're talking yellow radiation, but it emits infrared. All right, so again, if we do this same experiment, but now we get this curve. Okay, this is what we actually get if we do this calculation. You really sit down and do this if you want to do it. It's not too tough. And it's actually kind of interesting. It's a little bit unexpected. First of all, this is the current temperature. Okay, so it is cooler in the inner solar system. That is expected because, of course, the whole point is that we think that the solar nebula from which the Earth formed was a hot cloud of gas, right? Because it had gone through all this gravitational compression we're talking about and squeezing, so it heated up. So the early temperature near the Earth would have been higher. And look now, the red curve here at the Earth's location is below the freezing point of water, right? So now in the current solar system temperature we can get water as to the Earth. So this is what's happened. The thing I didn't expect was that there's this crossing out here. We actually see that the current temperature of the solar system is a little warmer in the outer solar system than it was in the early solar system. So this is kind of a little bit of a puzzler. And this actually gets us into talking a little about the sun, which is the main thing we're going to get into later. Okay, so again, the red curve is the current temperature as a function of distance from the sun. Blue curve, 4.5 billion years ago. It's cooler now in the inner solar system. We expect that. But it's warmer now in the outer solar system than it was. And this brings us to talk about the sun and the fact that the sun's own level of radiation output actually hasn't been a constant. It's been relatively constant for some time recently. But if we go back to early times, we're actually interested in the red curve, it turns out, the luminosity of the sun. Because remember, it's the brightness of the sun that's going to determine the temperature of some object in space. So we're looking at the red curve. Okay, so here we are now. This is us now, 4.5 billion years from the beginning. But back around the time that we're talking about formation of the solar system, we're only at about 80% of the solar output that we have now. Okay, so the sun was not radiating as much energy back then. So now let's look at these curves again. So what this is telling us is the reason that the temperature was hotter in the inner solar system back then, even though the sun was actually dimmer, is because of that heat that built up in the solar nebula from the gravitational squeeze. But the reason it's hotter in the outer solar system now than it was then is because the sun's actually radiating more now than it was then, about 20% more. So anyway, a little bit of stuff that's kind of an interesting way of comparing things. All right, so again, pretty much gone through all the words that are on here. We're going to form those iceberg-type objects in the outer solar system. Those are going to form the nuclei of the giant planets. And then the icy planetesimals are going to get flung hither and yon. Many, many, many of them, the majority probably, are going to be flung into the outer solar system to form the Oort cloud. A sizable fraction also stay in the Kuiper belt. That's where they form. That's where they live their whole lives in that particular case. And many come into the inner solar system and probably provide water to Earth. So again, if you remember the temperature curves, 4.5 billion years ago, too hot for water really to remain on Earth very much. But after the cooling took place, if we get the ice delivered by comet, I wonder if that was the inspiration for the new Amazon drones. Yeah? Deliver stuff like water. Very expensive bottle of water. I mean, you really have to be lazy to get an Amazon drone, drop a bottle of water in your driveway, instead of just going get it. Anyway, okay. And how can that be cost effective anyway? I did not figure that out. Like, that's not going to cost $100 to deliver by drone. But they might. I'm sorry. Okay. Before I go here. Okay. Well, basically, we're seeing again the icy fragments being flung, some out, some in, just depending on the details of their collisions with Jupiter, or maybe some with Saturn. Okay, figure from the book, seeing our icy planetesimals, some going to Kuiper belt, some Oort clouds, some just staying there, until we get this nice regular pattern that we see in the outer solar system, where the only icy planetesimals that are left are actually in the Kuiper belt, but they're not in that inner zone anymore. They've been flung somewhere at that point. Okay, so again, getting a little closer to talking about the sun. Young stars, as the sun was a young star 4.5 billion years ago, go through a period called a T-Tauri period where they actually have a very strong stellar wind, much stronger than the stellar wind that we see now coming from the sun. And that helps clear away some of the leftover remaining gas. That's part of the reason that we don't see more hydrogen gas in the solar system now. We see that when we look at other young stars. So the sun's solar wind right now isn't strong enough to clear out gas if there was any there now, but it was stronger back then, and that's part of the explanation. So there's many, many observations of systems like this so-called Herbig-Haro object here, which is actually an object that, we see that kind of curved greenish thing up there. That's a region that's being affected by a shock wave due to a very strong solar wind. from this very bright young star here.